Now in this problem, we have been given two solutions to the differential equation, y1 and y2. We're asked to verify that they are solutions and then find particular solutions of this form where we have our first term y1 times some constant plus our second y2 times another constant such that it satisfies these initial conditions. Before we get to this, let's just verify y1 and y2 are solutions. As we look at this differential equation, we can see it's a second order linear differential equation. So in order to verify that this is a solution, we have the original equation. We need to get to the second derivative, so we take the first derivative, 3e to the 3x. That tells us the second derivative is 9e to the 3x. Now let's verify, because it tells us if we have the second derivative, 9e to the 3x, and we subtract 9 times the first derivative, we should end up with 0. And indeed we do get 0, so we verified that y1 is a solution. We can similarly verify that the y2 is also a solution. y2 is e to the negative 3x. The first derivative, negative 3 e to the negative 3x. The second derivative, positive 9 e to the negative 3x. And then we just verify again. Take the second derivative, subtract it from 9 times the first. And we definitely would get 0. So we verified that these both are solutions to the differential equation. So now we're asked to find another solution to the differential equation, and particularly we're basing it off of our two previous solutions. And this is known as the superposition principle. So we are looking for another solution that fits this example. So we have c1 times e to the 3x plus c2 times e to the negative 3x. And by the superposition principle, we're guaranteed that this exists for this problem. We just need to figure out what should our constants be in order to fit these initial values. Okay. So let's check out the first one. Whenever we input 0 in for x, we should get a result of negative 1. So that gives us negative 1 equals c1 times e to the 0, because 3 times 0 is 0, plus c2 e to the 0. Now e to the 0 is just 1, so that just becomes c1 plus c2 equals negative 1. In order to use our next initial condition, we need to know about the derivative. So let's take the derivative of this. Y prime is 3c1 e to the 3x. Because the constant is there, as we take the derivative of e to the 3x, it's e to the 3x times its derivative, which is our 3. Plus, take the derivative of e to the negative 3x, that's e to the negative 3x, times the derivative of the inside, that's negative 3, all times our original constant, c2. And now when we plug in 0 to our derivative, we should get the value of 15. So we have 15 equals 3c1 times e to the 0, which is just 1, plus, or I should say minus, 3c2 times e to the 0, which again is just 1. We can drop that. And now we have two equations and two variables. We can solve those to determine what c1 and c2 would be. You can either use the elimination or substitution method here. I think I'm going to use the elimination method. If I multiply this one by 3, that gets me negative 3 equals 3c1 plus 3c2. Add the two equations together. We see the c2's cancel, and we end up with the equation 12 equals 6c1. That means c1 is equal to 2. Okay, now we can plug this back into the original equation, and we'll find what c2 should be. 1 equals 2, negative 1 equals 2 plus c2. That tells us c2 needs to be equal to negative 3. So our equation should be y equals 2e to the 3x minus 3 e to the negative 3x. Now here we have a similar problem as before. We've been given a second order linear differential equation. We have two solutions given to us. We need to verify that they are solutions. And then through the superposition principle, we need to find a third solution and then figure out what are the correct coefficients so that these initial conditions are met. Let's first verify y1 and y2 are solutions to the differential equation. So we need to know the second derivative. Let's take the first. The first derivative is negative sine of 5x multiplied by the derivative of the inside. Derivative of 5x is 5. So that's negative 5 sine of 5x. The derivative of that then we know the derivative of sine is cosine. So we have negative 5 cosine of 5x all times the derivative of the inside of the 5x, which is 5. And that will get us negative 25 cosine of 5x. And now let's verify. We have that the second derivative plus 25 times the original equation should get us equal to 0. So our second derivative, negative 25 cosine of 5x, plus 25 times the original cosine of 5x. Okay, that definitely is equal to 0, so we verified for the first y sub 1. Let's check y sub 2. The derivative of y sub 2 is cosine of 5x times 5, or 5 cosine of x of 5x. The second derivative then would be derivative of cosine is negative sine times the derivative of the inside, so we get negative 25 sine of 5x. Let's verify. We take the second derivative, add it to 25 times the original, and we do indeed get 0. So we verified y1 and y2. So we're now looking at this third solution, y, which is some constant times the first term, cosine of 5x, plus some other constant times the second solution, sine of 5x. And we know it has to fit these two initial conditions. So first off, whenever we plug in 0 for x, the result should be 10. So let's write that out. We have 10 equals c1 times cosine 5 times 0 is 0. Cosine of 0 is 1 plus c2 times sine 5 times 0 is 0. Sine of 0, if we think of the unit circle, is 0. So this becomes the equation 10 equals c1 times 1. So c1 is equal to 10. To use the next initial condition, we need to know about the derivative. So we take the derivative, and that is 5, negative 5, c1 sine of 5x, plus this derivative is 5 c2 cosine of 5x. Now when we input 0, we know the result would be negative 10. Sine of 0 is 0, so that whole term goes away, plus 5c2. Cosine of 0 is 1, so we get negative 10 equals 5c2, or c2 is equal to negative 2. So next up, we're asked to determine whether the pair of functions sine squared of x and 1 minus cosine of 2x are linearly independent or dependent on the real line. Now, in this case, the idea of linearly independent or dependent functions all comes down to, as a quick test, can we write one function as a constant multiple of the other one? And in order to answer that, well, we'll want to remember for this particular problem a really nice trig identity. that sine squared of x is equal to 1/2 times 1 minus cosine of 2x. So from this trig identity, we know that I could write f of x as 1/2 times g of x. By this, they are defined to be linearly dependent, because I can write one as a constant multiple of the other. As we think about solving this differential equation, we always try to characterize it in our mind. And as we look at it, we can see very clearly it is second order. Additionally, it is linear. And it has constant coefficients. So the only coefficients to our second derivative, our first derivative, our y term are constant values. So this is what we would call a homogeneous second order linear differential equation with constant coefficients. And whenever we recognize that, we remember the idea of the characteristic equation. Now, before we get to how we work with the characteristic equation, let's try to give some background about why this works, just as a quick review. Looking at this differential equation, it's saying we should be able to take the original function, multiply it by 15, add 2 times the derivative, plus the second derivative, and end up with 0. So basically that's saying that the second derivative plus 2 times the derivative plus minus 15 in the original will equal 0 together. So as we're thinking through what could possibly be a solution to that, we realize that a good candidate could be something that doesn't change much when we take the derivatives, except for maybe changes by a constant, and we could find the right constants that would satisfy this equation. Now that brings to mind a solution that we saw earlier in these videos, which is e to some constant times x. Now if this is a solution, let's just suppose that is a solution that fits this. We know that under derivatives it remains very similar apart from constant multiples. Then the first derivative is r times e r to the x. Second derivative is r squared e to the rx. And that would give us the equation. The second derivative becomes our r squared e to the rx, 2 times the first derivative, minus 15 times the original. And what we notice here is because the original function, the derivative, and the second derivative all have the same e to the rx term, what we could do is we could factor that common term out of the left side, and we get this equation. Now think about whenever you have a product of something equaling 0, that can only happen if one of the two pieces of the product or both equal 0. Think about what you know about the graph of e to some number times x. We know that that's never 0. So if this product equals 0, it has to come from this quadratic part. This will only occur when this equals 0, and what that's really getting at is, if you notice, the coefficients are exactly the same as here. 1 times the second derivative, 2 times the first derivative, negative 15 times the original. This is our characteristic equation, and what it's doing is it's saying we have to find a way to weight the coefficients in such a way that when we multiply it by the second derivative, the first derivative, and the original, they will cancel each other out and bring us to 0. So solving this differential equation is figuring out what R values could make this true. Well, this comes down to a factoring problem then. We think about how to factor this, what multiplies to give us negative 15 but can add to give us positive 2. That's R plus 5 and R minus 3, which gives us the two R values of negative 5 and 3. So we have the two separate solutions that y could equal e to the negative 5x or e to the 3x, and we know from our superposition principle we have the solution c1 times e to the negative 5x, that's our solution for this term, plus c2 times e to the 3x. And if this problem gave us initial conditions, then we could solve to determine exactly what our constants c1 and c2 should be. Now, as we look at this next differential equation, we see that we're in a similar case as what we dealt with before. This is a homogeneous second-order linear differential equation with constant coefficients. So we immediately think through the process and go to our characteristic equation. So in this case, we're going to ask ourselves, we know our solution is something of this form. We need to find what that r value is. So we have the equation 9 times r squared, so 9 times, that comes from our second derivative, minus 12 times r plus 4. When is this equal to 0? Let's think about factoring this. So we need something that multiplies and gives us positive 4. We can see the middle is negative, so we know we're dealing with two negative terms. Let's try 2 and 2. Similarly, let's try 3r and 3r. That will give us our 9r squared, so let's verify. 9r squared minus 6r, those do combine to give us our negative 12r, plus 4. So this is our solution. And what we find is we don't have two distinct solutions. We have r equal to 2/3 for this and this one. So we have a repeated root. And if the characteristic equation has a repeated root, then we form our solution as y equal to c1 plus c2 times x times e to the repeated root. So for our problem, our repeated root is 2/3. And this will be our solution to the differential equation.